Hi, hello everyone. My name is Umaima Khurshid and I will be starting our presentation. So, our project is titled Temporal and Category Based Price Similarity Network Analysis. In simple terms, we wanted to understand how similar Pakistani cities are in terms of their price behavior and how these similarities change over time. To do this, we used CPI data, which basically tells us how prices of essential goods and services change month to month. Now, every city has different buying patterns and different price levels. So, we thought, what if we measure how similar these patterns are? If two cities behave the same way, maybe their markets are strongly connected. And if not, that tells us something too. We approached this from a discrete structures perspective. That means instead of doing traditional economics, we use tools like cosine similarity, graph theory, and partial orders. This allowed us to convert real economic data into a mathematical network. To explain our data briefly, we took monthly CPI prices for multiple Pakistani cities over 2 years. We grouped the products into seven categories: things like food staples, meat and dairy, utilities, and so on. For each city and each category, we formed a 12-dimensional vector, one value for each month. But before we could do any math, we needed to clean the data. Some values were missing, so we used forward fill, backward fill, or mean imputation. If a product had too many missing values, more than 20%, we removed it to avoid bias. And because categories have different scales, we applied minimum maximum normalization. This step is really important because without it, the cosine similarity wouldn't be meaningful. Speaking of cosine similarity, this is the core mathematical tool we used. If the angle is small, the vectors are very similar. In our case, that means two cities had very similar price movement patterns throughout the year. After normalization, the values lie between 0 and 1, where 1 means extremely similar. So, what we did is compute cosine similarity for every pair of cities, for every category, and for each year. This gives us a full matrix of how cities relate to each other. And this similarity matrix becomes the foundation for our graph construction, which my teammate will explain next. Before I hand it over to the next presenter, I will quickly explain my part in the code. In the programming, I handle the uh, data loading and processing section. First, we read the CSV files using pandas and group the data by city and category. Then missing values are filled using forward fill, backward fill, or mean filling. After that, I applied minimum maximum normalization, which scales all values between 0 and 1. This is important because cosine similarity depends on scale consistency. Then comes the cosine similarity function. In the cosine similarity function, I calculate the dot product of vectors and divide it by their magnitude. This gives us the similarity matrix for each category and year. So basically, my code prepares the data and computes the similarity values that the entire project is built on. Now, I will pass it to the next presenter who will explain how these similarity values are converted into graphs and how we analyze changes over time.
Assalamu alaikum everyone. As Umema said, I'll be explaining the modeling part of our project. Once we get the cosine similarity for every category and year, the next step was to convert them into graphs. So basically, each city is a node, and we draw an edge between two cities if they are similar enough. For similarity, We used a threshold that was either zero point 0.6, 0.7, or zero point 0.8. A lower threshold gives you more edges because even moderately similar cities get connected, and a higher threshold only keeps the strongest relationships. This let us compare dense and sparse networks across categories. Each edge carries a weight, which is the cosine similarity value. So, stronger similarity means a stronger edge weight. When we visualize these graphs, as you can see on the slide, you can clearly see clusters forming. For example, some cities always stay close because their price behavior is very correlated. Now, because our project spans multiple years, we wanted to understand how these networks evolve over time. This is where our temporal relation comes in. For each category, we created a relation called T between the graphs of different years. Formally, we say one year is related to another if the earlier year's edges are a subset of the later year's edges. The interesting part is that this relation actually forms a partial order. And we proved that by showing it satisfies the three properties of reflexivity, antisymmetry, and transitivity, as you can see on slides. Once we established that, we visualized this using a Hess diagram. In a Hess diagram, each node represents one year's graph, and arrows only appear where one year directly grows into the next without any intermediate steps. Since we only have 2 years, you either get a single arrow or no arrow if one year does not include the other. As you can see on the slide, that the arrows don't include in the first one and do include in the second one. These diagrams helped us see whether cities become more similar over time or if the relationships actually weakened. In some categories, the networks become denser, suggesting convergence. In others, opposite happened. All of this sets the stage for analyzing centrality. Before passing on to Farwa, I would like to explain the code. In the code, the entire process was implemented by filtering edges using thresholds, as I mentioned earlier, generating adjacency list and comparing edge sets. We then draw the Hess diagrams to visualize the structural progression. This this brings us to the final and most important analytical part, that was identifying influential cities, for which I would be passing on to Farwa.
Assalamu alaikum everyone. I am Farwa Fatma and I'll start by explaining my part in the code. In my section, I calculated all four centrality measures using network X, degree, closeness, betweenness, and eigenvector centrality. These are computed separately for each graph. Then I normalized all centrality values so they could be compared fairly. After that, I applied entropy based weighting where matrices with higher variability receive higher importance. Finally, I computed the overall influence score by multiplying centrality values with weights and summing them. The results are saved and visualized using heat maps and graphs. So this part of the program converts a raw graph structure into meaningful rankings and final results. Now I will be also explaining our centrality analysis, weighting system, and final insights. Once the graphs for each year and each category were built, we wanted to understand which cities are the most influential in terms of price behavior. To answer this, we calculated four different centrality measures. The first is degree centrality, which simply counts how many strong relationships a city has. If a city connects to many others, it means its trends are closely linked with the rest. The second is closeness centrality, which tells us how quickly a city can reach other cities through the network. Cities with high closeness are well positioned in the structure. The third, betweenness centrality, measures how often a city lies on the shortest path between other pairs. If a city has high betweenness, it acts like a bridge or connector in the market structure. And finally, eigenvector centrality measures not just connections, but the importance of the nodes it's connected to. So, being connected to influential cities increases your own influence. Now, instead of treating all the centrality measures equally, we applied entropy based weighting. This gives more weights to the matrices that have higher variability because those matrices contain more information. We also compared this to simple equal weighting to show the difference. Using these weights, we computed an overall influence score by each for each city across categories. and then combined category scores to get a final aggregate influence ranking. We also created heat maps and network graphs to visualize these results. The heat maps clearly show category specific patterns, while the network graphs reveal which city consistently appear in the core cluster. Finally, in our conclusion, we highlight that this project combines real economic data with discrete mathematics in a meaningful way. By using cosine similarity graphs, centrality, and partial orders, we get a structural understanding of market relationships that traditional analysis does not provide. Overall, we found patterns of economically similar cities, category based clusters, and temporal shifts in similarity networks. The method is general, scalable, and can be applied to other datasets as well. Thank you very much.